welcome to the Monday video for the week of March 23. In this particular video we're going to be working on section 3.5. I know we have started 3.5 and had some of that done the week prior to spring break, but I want to make sure that everything's coming together and working on section 3.5 because it will be part of what is on the quiz coming up this Friday. There are two things due this coming Friday, which is Friday, March 27th. First, there's the homework. There is homework for section 3.5. It's posted on My Math Lab, which is found in your Canvas account. On the left-hand side, you press the tab that says My Math Lab, and then it'll take you to a page where you click on kind of an orangish-colored button, and that'll then take you to the My Math Lab materials. The section 3.5 homework allows, I believe it's 2 attempts for each answer. It is due at 1 p.m. on Friday, the 27th. You can do things late, but be aware that if it is done late, there's 50% off on the grade for that particular homework. So you really do want to get it finished before 1 p.m. on Friday, March 27th and have it submitted to the online system. The second thing to remind you of here at the start of classes on Monday is Friday there will be a quiz. Exactly what time it will be made available to you online and what sections it will conclude will be announced on Wednesday. So you have to stay tuned for that to find out when and where the quiz is going to be. Let's take a look at the material in section 3.5. We did some of this last week. The main objective in section 3.5 is to look at some applications of exponential functions. These are going to be applications that will affect you, that do affect you now, and will continue to affect you throughout the rest of your life as far as your finances go. There are several different ways that interest is either charged or credited to you. Now remember, interest can either work for you or against you. If it's in the form of a loan, it's working against you because it's extra money that you are paying for the privilege or the opportunity of receiving a chunk of money up front. So you're paying for the opportunity to have that money now instead of saving up and having it later. The other way that interest works is when you save money, invested in a retirement fund or other things that we'll use as examples throughout this section. The institution that you're giving the money pays you interest so that they have the opportunity to use that money for a period of time. Let's take a look at a couple different ways that interest can be either charged or, more hopefully, accumulated into your accounts. Interest can be paid or charged in a variety of ways. It can be done annually. This is also known as simple interest, and this is something that we did work on last Friday, and I'm not going to go over that again because that is pretty straightforward, and if you need to review how this works, you can review that particular movie. What I want to look at is if the interest is applied other than just once a year. So for example, it can be semi-annually. This would mean it's twice a year. It can be applied quarterly, which would mean it's 4 times a year. It can be applied monthly, which would mean that the interest is going to be paid to you each month, or 12 times a year. Or sometimes you will find things that are done daily. That's kind of unusual at this point because they usually go to continuous compounding. But with daily, that means you're going to receive interest 365 times. This year is a leap year, so you would receive interest 366 times. If you're working with any of these scenarios here, the formula that winds up being used to compute the total amount of money at a particular interest rate compounded one of these numbers of times a year is the amount that you have at some point in time, and t is going to be in terms of years. Now be careful, because if it's 6 months, t equals 0.5, because 6 months is half a year. So it's going to be a evaluated at t equals p sub 0 times 1 plus r over n to the nt. And yes, you do need to be familiar with this formula. You do need to be able to use it and plug it into your calculator. Okay. Well, what are the things you're plugging in? Okay, so let's take a look at this formula. P sub 0 is the amount you invest at the start. R is the interest rate. Now please note this, it's the interest rate as a decimal, not as a percent. So you need to convert it from a percent back to a decimal. So for example, if it's 4%, 4% would look like 0.04 because per cent, the cent part of that means 100. That means slide the decimal over 2 places because 2 digits or 2 decimal places is 100. N is going to be the number of times a year that the interest is compounded. I'll just abbreviate compounded. And T is going to be the number of years. So if it's something relatively short term, like you're making an investment that is going to last 5 years, T would be 5. If you're investing in retirement, it might be 40 years till you retire, in which case T would be 40. Let's take a look at a first example. So here we go with example 1 on how to compute these. Now it's very important that you actually follow along and do these computations in your calculator, because on the quiz Friday, you're going to have to be able to do them on your calculator, and you're going to have to know how to do this on your own without help. So this is the opportunity to get help to compute these things. Okay, so let's say we have $100. Just take something simple. And it's going to be invested at 4%. And the interest is going to be paid quarterly. Okay, so let's go through this and let's identify some important parts about this. Not 100%, this is going to be $100. I was thinking ahead to the percentage. The $100 is your P sub 0. The 4% tells you that R is going to be, as we just discussed above, 0.04. The quarterly tells you that you're going to get paid 4 times a year, so N is equal to 4. Okay. So here's the initial information that you need to get started on this. Now I have a table down here, and I'm going to move this table a little further down so it's not in our way right now. Because what I want to do right now is to look at how would you plug this into the formula that we have to work with. Well, if you'll recall, the formula was the amount that you're going to have at any time is P sub 0 times 1 plus R over N raised to the NT. So the amount that we're going to have at any point in time is equal to P sub 0. Well, that's the amount you start with. That's going to be 100 times 1 plus R over N. R is this 0.04. N is this 4 here. And then we're going to have it raised to the N. Well, we already know that that's 4 times T. We haven't talked about how many years that's going to be. this point in time, what I would suggest that you do with your calculator is to leave the 100 outside, and using the order of operations, please excuse my dear Aunt Sally, the P means parentheses, evaluate what this is. So go ahead, pause the movie for a moment and plug that in on your calculator. What you're going to do is 1 plus 0.04 divided by 4. And I'll tell you the answer here after you've paused it and done it. The answer should be 1.01. Now we're going to have this to the 4 times t. Okay. So we can work this a little bit further, and we're going to have the 100. We can do the 1.01 raised to the 4th power times t, but what we can do is we can take and evaluate this. And when we do that, we're going to have 100 times some number, and we're still going to have t as an exponent. So go ahead and take the 1.01, raise that to the 4th power on your calculator. Pause the movie, do that, and turn it back on when you get an answer. Okay, we're only going to use 3 digits. Okay, we'll go 3 digits on each of these computations. And what you should wind up with is 1.04, and it goes 0.6, but 0.6 is going to round to be 1.041. Alright, so this gives us then a formula that we can use to compute how much money is going to be in the account at various points along the way. So for example, the table that we have down here, and I'll go ahead and I'll move it up a little bit now, so we're ready to use that. We can evaluate for year 0. Alright, so let's go ahead and use this function to evaluate what the balance is going to be at these different points in time. At 0, this means t equals 0, so we're going to have 100 times 1.041 to the 0 power. And remember, any number raised to the 0 power is just 1. Okay, so this is just going to work out to be 100, which makes sense. If there's $100 and it's not been there any time, it's not accumulated any interest. At t equals 1, we're going to have the 100 times 1.041 to the 1st power. Any number to the 1st power is just that number, so we're going to have 100 times this. Well, you don't need your calculator for that. You just move the decimal 2 places, and that's going to give you 104.1, which doesn't make a lot of sense because we're talking dollars and cents, so we'll fix it like that. Remember, since we're talking dollars and cents, we're going to need 2 digits of accuracy for every value we report in the balance. Okay? At 2 years, this is going to be 100, and you're going to have the 1.041 squared. So we can do the 1.041 squared, and that's going to give us 1.084 times the 100 is going to give you 108.37. And you can continue on with these. 1.041 raised to the 3rd is going to give you 112.81. The thing to notice is basically every year you're getting $4 plus a few cents extra, and the number of cents extra is increasing as the years go on. Now, this may not look like a significant thing with a small initial amount of money, $100, but as you get into a career job and you're able to put more than $100 in, this can really grow quickly. Okay, now one of the things I want to point out to you here, and we've already seen it in this particular example, is as we went down through and we simplified things, we came up with this number here. This number here is going to give us what is called the effective yield. We can use that to compute the effective yield. Because the interest is compounded several times a year, you're going to receive interest on the money that you've invested, plus you're going to receive interest on the interest from the last quarter. That explains why this does not just go up $4.10, but this goes up $4 and, well, it's an extra 27 cents over what this increase was. This was an increase of $4.10. This was an increase of $4.27. And you'll see here an even higher increase with this. It's going to be $4.44. That increase in the amount of money that you're getting each term is related to the fact that you're getting interest on the interest. The effective rate is going to be 1.041, and we're going to subtract 1 from it, because remember up at the beginning we added 1. Okay, so we're going to subtract 1, and this is going to give us 0.041, which is, as a percent, 4.1%. The effective yield is this 4.1%. Now notice, when we started this problem, the interest rate that we started working with wasn't 4.1%. The interest rate that we're actually working with is 4%. However, because the interest is paid on the previous quarter's interest, it actually grows at a rate faster than 4%. The effective yield, what it's actually going to behave like, is if you were getting 4.1% a year annually. This ability to compute an effective yield is very important, because what will happen is, let's say Bank 1 offers you 4% quarterly, and let's say Bank 2 offers you 4.2%, but it's annually. And let's say Bank 3 offers you, let's see here, 4.1% daily. And you need to figure out, well, gosh, which of these am I going to want to invest in? Well, because they are compounding interest at different rates, quarterly, annually, and daily, it's hard to tell how much you're really going to get from any one of these by the end of the year. Okay. We do have some information here, though, on what the yield is going to be. What we want to be able to do is to compare the effective yield. Now, we've already looked at what the effective yield would be like from Bank 1. It would be 4.1% if it was back to simple interest. Bank 2 is simple interest, that's 4.2%. Then when we go through the computations to compute the effective yield on Bank 3, that's going to look like 1 plus 0.041 over, we're going to use 365 because it's daily, and then raise it to the 365th power. This actually works out to be, after we subtract the 1 from it, a rate of 0.041849. Okay. This would also advertise to have an effective annual yield of 4.2%, but realize that when you actually compute it, it's slightly less than 4.2%. So of these three options, the one that's actually going to give you the highest yield per year is this one. And it's very difficult to actually ascertain which is going to be the most profitable way to invest your money if you're just given this information here, and that information is going to vary from one bank to another. What you really need to do is to compare the effective yields. By comparing the effective yields, you can then bring everything back to the same standard. What you're doing is you're converting all these other rates of interest payment back to simple interest. Okay, so being able to compute an effective yield is very, very important to you. It'll allow you to figure out where your money is best invested, and that'll make a big difference over a period of 30 or 40 years of investing. Okay, let's practice another one of these effective yield problems. In this case, let's compute the effective yield This is also known as R sub E, so it's the effective rate, okay, at, let's say, 4.5% compounded monthly. Go get them. Put the movie on pause, calculate this yourself, and then when you've calculated a value for the effective yield, turn the movie back on. And if you need to review how to compute that, that's fine. Just back the movie up a bit, watch that portion, do the computation, and then come here and check to see how this works out. Okay, so hopefully you've actually done the computation yourself. The effective rate is going to be the 1 plus 0.045 divided by, in this case it's compounded monthly, so it's going to be 12 times. It'll be raised to the 12th power. Then the last thing we'll need to do is to subtract a 1. Okay, to work this out on your calculator, the first thing you do is you take the 0.45 divided by 12 equals, add the 1 equals, now at this point you should have 1.00375, raise that to the 12th power, and what you should wind up with here is 1.0459398, and it goes on, so we'll just leave it like that. Remember that as you're computing the effective yield, you need to subtract 1. Remembering to subtract 1 is very important. Okay, so stick with that. This will then give you an effective yield or an effective rate of 0.0459, which means that you're really looking at about a 4.6% annual yield on this investment. Okay. Now, we could take this effective yield a step further. Suppose that interest was paid every hour on your account. That may sound kind of crazy. Doing it every day sounds perhaps a little ambitious, but we could compute the effective yield at 4.5%. We'll compare it back to what we just did. Okay, so remember we did 4.5% compounded monthly here. Let's do 4.5% compounded hourly. First thing we have to do is figure out how many hours there are in a year. Well, that's not too bad because there are 24 hours in a day. Hey, this takes us back to the stuff that we were doing at the beginning of the semester, doesn't it? Times 365 days per year. Okay, Okay, the days will cancel. And this is going to give us hours per year. So what we're going to do is we're going to take the 24 times the 365. And if you remember back, we actually did 365 and a quarter, but we're just going to let it run like this. This is going to be hours per year. So now the effective rate or yield could be computed as 1 plus the rate 0.045, converting back from a decimal or to a decimal from a percentage. And this time we're going to divide by how many times has this been compounded. Well, if you're getting paid every hour, there's going to be 8,760 payments a year. So we raise it to that power. And remember to subtract the 1. So what I'm going to do now is I'm going to take the 1 plus 0.045 divided by 8,760 equals, and that's going to give 1.000005. We're going to raise that to the 87/60th power, and what that winds up giving us here is 1.04602777. Of course, we have to subtract 1, which is going to give us 0.04602777. If you were to look at a bank ad, this would say 4.6%, just as would the previous result. However, notice, even though the ad's going to say that, they're rounding off. Okay, they are rounding off. Which one actually pays more? Well, if you compare them in the thousands place, okay, what we're going to have in the monthly is a 5, whereas here we have a 6. So you can see that compounding hourly actually pays a little bit more. Huge amount more? Not really, but it's a little bit more. This paying hourly idea is very, very close to the idea of continuously paying. If you're continuously paying interest, that means that every second you get interest. That is also called continuous compounding. You could do this using the previous method, doing it every second. Figure out how many seconds there are in a year, just like we did how many hours, and plug those numbers in and let it fly. However, we're going to wind up moving to a completely different formula. In this formula, where the amount that you have at some point in time is going to wind up being the amount you start with, e to the RT. Now, e was developed by a mathematician by the name of Euler. And where e comes from, e is actually a number, just like pi is a number, 3.1415926, something or other. Okay? E is a number as well, 2.71, I forget what it is. Okay? But where e comes from is by going back up here to our initial formula. This formula here without the t, just a raise to the n. And if you let n go to infinity, okay, get really big, the value that you get, and there's some mathematics that will allow you to do that. We're not going to work with that here or worry about that. But if you do that mathematics, it'll give you this number, this value here that's e. Okay. What we can do here is we can figure out how much would you wind up making if you were to invest it in an account that has continuous compounding. Most banks have gone to this for in the investing side because it's no more difficult for a computer to run this formula than it is to run the previous formula. So as an example of how to apply this, what we can do is we can say that we have $100 at 4% compounded continuously. as with the earlier one, we identify our initial amount of money. There it is. We're going to identify our interest rate. There it is. And let's say for 1 year. So that we now have a time frame, T. So when you're given the problem, you want to first find out, is it a situation where it's compounded continuously? If it is, here's the formula you use. If it is not compounded continuously, you go back to that earlier formula that we were looking at, determine how often things are compounded, and you go with that. Okay? So here we have a continuous compounding. We're going to figure out the amount of money that we have in 1 year. That's going to be the $100 times e to the interest rate 0.04 times 1, the amount of time it's going to be there. On your calculator, okay, your calculator is going to show one of two things. It's either going to have a key that says e to the x, or it's going to have a key that says ln of x. And if it says ln of x, up above it, it's going to say e to the x. So for this, you would first have to press the key second, and then press this key, and that'll give you a natural log. All right, so let's figure out what this is going to work out to be. We're going to have 100. Well, I'll tell you what, let me do this first. We're going to do e to the 0.04. This portion right here, right there, is going to give you 1.0408. Going to take that times 100. Now I'm not worried about raising it to this exponent, because when you raise it to the first power, you just get back what you had. So we would have the 1.0408 to the first power, which is 1.0408. We're going to multiply that times 100, which means slide the decimal over 2. So we're going to get $104.08 when you slide it over twice. Now notice here the interest that is paid is going to be $4.08. If we compare that to the earlier result, this is interesting. Okay, I did some rounding. Things were rounded a little bit differently here on this one. And this wound up being a little bit higher. Actually, it should be the case that the continuous compounding is going to pay slightly more. The difference is due to the way I rounded the numbers. Okay. If I was to round this to 3 decimal places, this rounded to 3 decimal places would be 1.041, which would then give us $4.10 interest, which would tell you that the interest rate is basically the same on that amount of money for that amount of time. If you're asked to compute the effective yield and you're doing continuous compounding, okay, remember we're going to be using the amount at time t equals the initial amount e to the rt. Now, we're going to use the same strategies we did earlier. Recall earlier, to get our effective yield, let's see, where was that? Up higher. We used this portion here. See that? We used everything inside the parentheses, as well as the 4. Down here, we don't have a whole lot inside of the parentheses. It's just E. E is doing all the work of everything inside the parentheses. But this part here is going to allow us to compute the effective yield. In in this case, our effective yield is going to be e to the r, and of course we have to subtract the 1 again. So to compute for this problem, it's going to be e to the 0.04 minus 1, and this will give us then an effective yield of, let's see if we do e to the 0.04, we get 1.0408, and then when we subtract the 1, we're going to get 0.04081, and if we round it off to 3 digits, as we did earlier, the effective yield is going to be 4.1%. Okay? If you take it out past 4 digits to 5 or 6 digits, you'll find that in a continuous compounding will allow for slightly faster growth, slightly higher accumulation of interest than something done monthly. Let's take a look at another example here. Historically, that means over the last 100 years or so. Right now the stock market is having a bit of a struggle with all this craziness going on with the coronavirus. But historically the stock market yields a little over 10% annually. And in your book I believe they listed as 11.7%. So we'll go with this. And this is per year. So if you take money, invest it into mutual funds and things of that nature, and allow that money to ride for 30 or 40 years as part of your retirement account, in 30 or 40 years this will have had time to grow where it's continuously being compounded. And the question is, okay, let's say you're on your career job and you put some money away each month. Let's say you invest $500 each month toward retirement and your company matches. Or let's say even $450 and your company matches, which will give you about $900 a month going in. And that'll give you right around, let's say, $10,000 a year. So let's say you invest this $10,000. Now remember, you only had to do half of that amount, because when a company matches your retirement, whatever money you put in, they put in. Typically, that's only up to a given percentage of your income. Okay, but you definitely want to take advantage of that. Okay, and we've talked about that before. If you invest $10,000, let's take a look at what that's grown to in 30 years. And then we'll take a look at what it's grown to in 40 years. These are time frames that are more likely to be reasonable for retirement. So what we're concerned about here is how much money will you have in 30 years. Now remember, this is not a times 30. This reads the amount in 30 years will equal to this $10,000 that you put in, e to the 0.117, the interest rate, times, and it's going to be times 30. Okay? Because you're going to be investing, in this case, for 30 years. Okay, so what's this going to work out to be? Well, it's going to be 10,000. On your calculator, you can fire that pupper up. We're going to do e raised to the 0.117 times 30 equals, and what this works out to be is 33.4482678. We'll round it off there. Wonder what that is. Well, I'm going to multiply that times 10,000. And what that gives us then is $334,482.68. The thing to remember here is this is not your total savings toward retirement. This is just what you put in the first year. The second year, hopefully you'll put in a little more than $10,000 because you'll get some kind of a raise, hopefully, if you're doing a good job and working hard. And what will happen the second year is it won't be in for 30 years, it'll be in for 29, so it won't accrue quite as much interest, but you're going to have another $300,000. So if you save 2 years into a retirement account, you've already got over $600,000, which is well over $500,000. million. And I think you can play this out in your mind and realize that, if you do this for all 30 years, even though you were never a neurosurgeon or something like that makes a huge amount of money, you can still retire with a very good retirement account. If we do this for 40 years, well, you figure it out. Put the computer on pause, and you figure out if you were to invest $10,000 into the stock market and assume that it continues to do 11.7%, how much would this $10,000 grow to in 40 years? Okay, hopefully you paused the movie and actually computed it yourself instead of just letting it roll, because you need to be able to do these things on your own, and the only way you'll find out if you can is by actually doing them. You don't want to find out on the quiz. It's the first warning that, I don't know how to turn my calculator on, let alone how to put this in. So let's take a look at what's going on here. The amount of money that would accumulate over 40 years is going to be the initial $10,000. It's going to be E raised to the interest rate 117 times 40. So what I'm first going to do is I'm going to bring down my $10,000 and I'm going to evaluate E raised to the 0.117 times 40. When you raise that to the 0.117 times 40, whoa, this is going to be 107.7700. That should be a 0, even though it looks like a 6. Let's say 7.3, and we'll cut it off there. Take this now times the 10,000 equals, and what you wind up with is 1077700. It says 723. I'm just going to round it off to 73. Well, wait a minute. That's only $100,000. In 30 years, we had $300,000. What happened? Actually, this isn't $100,000. You start figuring it out. Whoa. That first year's investment will have grown to over $1 million. So if you just do that for 1 year, work 40, there'll be $1 million in retirement. Ta-da, you're a millionaire. Of course, it would be nice to have saved a little bit more, because I suspect things will get a little more expensive as the years go on. There's one last thing we want to take a look at here in section 3.5. And that last thing is what's called the doubling time. Doubling time looks at how long does it take for the amount of money that you've put in to double in value. Talking about that $10,000, how many years would it take for it to double to $20,000, to $40,000, then to $80,000, then $160,000, and you get the idea. There is a rule of thumb. The idea of this is to allow you to be able to, in your head, estimate about how long it would take to double. And what that rule of thumb is you take 72 and you divide it by the interest rate percent. So for example, the doubling time at, let's keep it simple right now, 6% interest would be equal to the 72 divided by 6 for the 6%, which is 12 years. So if you have money invested in a situation where you're getting 6% interest, it's going to take about 12 years for it to double. Now, if we look at the stock market example, we'll round that off a little bit. And let's say that the interest rate is 12%. Some years it's better, some years it's worse, but it works out to be about like that. In this case, the doubling time is going to be the 72, and we're going to divide it by the 12, which would be 6 years. So that means your money will double in value every 6 years on average. try one, just to make sure this is working for you. Let's say that we have an interest rate of 8 years, or 8 years, that's wrong, 8%. Don't depend on this answer being 8 years, it's not. Compute the doubling time. Put the computer on pause. Compute the doubling time for an 8% interest rate. Alright, so hopefully you actually did put it on pause. This is going to be 72 divided by 8. And when you take the 72 divided by 8, you wind up with 9 years. So if you have money invested in a situation that's paying 8% interest, about every 9 years, the value of that money will double. Okay, this should give you some information that will allow you to get started on the homework for section 3.5. We need to do one more thing, and that's looking at computing how much time it takes, or computing T, and we'll do that at the start of the next movie. Okay? But you have enough information to start on the homework.